Right, our last set of nucleophiles are carbon-centered ones. With carbon nucleophiles, we've already actually seen one of these before. We've seen the Grignard reaction, right? We've seen how Grignard reagents can react with aldehydes and ketones to make alcohol, right? That's one of the ways we looked at. So, if you take your happy aldehyde or ketone, treat it with, how about an ethyl Grignard reagent, you will end up making, well, first you'll make your alkoxide, and then you'll go ahead and protonate it. Usually step 2 will be an acid wash or just water, and that's usually enough to protonate this. And so step 2 will just protonate, and you'll have it. So you can add a carbon nucleophile to an aldehyde or ketone. Works great. Remember, again, the Grignard reagent cannot be used in the presence of any proton source. So remember, it is very strongly basic, so we're going to be careful about this. So don't forget, you'll also need that acid wash because the first step gives you the alkoxide. The second one, once you rinse it with water, work it up with water or acid, you'll protonate your molecule, making it into an alcohol. So we've seen the Grignard reaction before. Another one that's going to be new for us is going to be forming a cyanohydrin. And so in this case, we're treating our aldehyde or ketone with HCN, and typically also you'll put potassium cyanide or sodium cyanide as well. But actually, that's fine together, and then we will end up with a hydroxy as well as the nitrile. So a C triple bond N. We're going to study reactions of nitriles in the next coming chapters, so we will see other things we can do. But this is exceptionally useful because you add just one carbon, which has a lot of functionality. The Grignard is a little bit tougher because you're just adding alkyl groups. Alkyl groups don't do anything. But now you're adding a carbon that has functionality, because we'll see what we can do with nitriles. We can reduce them to amines. We can hydrolyze them to make carboxylic acids. We can do things with nitriles. So they're particularly useful. We don't really have to worry about mechanisms here, but suffice it to say CN minus attacks the aldehyde, opens it up, and then you get a proton from the HCN. You may also see this reaction is also done with conditions of a different acid and your cyanide source. So that'll work as well. And so with this, you'll end up adding one carbon to your aldehyde or ketone. Apparently I've added 2 because I can't remember to write H. And with that, it already contains a lot of functionality, so we can do a lot of stuff with it. So, very synthetically useful. This is called a cyanohydrin. So cyano, of course, the CN, and then hydrin, just like we saw halohydrin formation last semester. So, those are the 2 easy ones. Always being worried, right? We have one more, which is called the Wittig reaction. And the Wittig reaction is one that won the Nobel Prize because it's incredibly synthetically useful. It's still very much used. There are a lot of variations on it that have improved it, because this was originally in the 70s, 80s, somewhere around there. And so a very useful reaction. What you end up doing is you take your aldehyde or ketone, and you're going to take what's called a phosphonium ylide. I'm going to just put, we'll put 2 methyl groups on this thing. In the presence of this reagent, which is called a Wittig reagent, which we'll look at shortly, what you end up doing is you end up attaching your carbon now right where the oxygen is. So you essentially replace your oxygen with an alkene with whatever groups you happen to have on it. So in this case, they were both methyl groups. And again, I seem to have forgotten another hydrogen. And we're going to see stereochemical considerations here, because in this case, we're actually able to control E versus Z alkenes that are formed by looking at our Wittig reagent. If we wanted to make this reagent, we simply take an alkyl halide in the presence of base. Not something I'm going to make you do, so don't worry about it, but if you want, it's in the book. You can go ahead and look at how to form Wittig reagents. But let's look at that reagent more closely. And we can also look at the mechanism of this reaction. This is what's called an ylide. Because while we see it as a phosphorus with its phenyl groups, what really happens is we have the resonance form that has the carbon with the negative charge, and it's stabilized by the heteroatom, the phosphorus, with the positive charge. And that phosphorus has 3 phenyl groups on it. There are variations, of course, of what ligands you have on the phosphorus. I'm going to just move that arrow. But we see here we have a negative carbon next to a positive, directly attached to a positive heteroatom, and this is called an ylide specifically. So it's a special case of Zwitter ion. Remember, Zwitter ions had both positive and negative in the same molecule. An ylide has them right next to each other, and they're different atoms. So we have a carbon and a phosphorus in this case. And so we can see here that in the resonance form, that carbon, which has the negative charge, is going to be nucleophilic. So it's going to go ahead and attack our aldehyde. So we have, we have our oxygen here. And I'm going to go ahead and draw it as the ylide form with the negative charge there. These 3 phenyl groups don't really matter, so I'm just going to keep them as pH. They're not really terribly important. And what's going to happen here is we're going to go ahead and attack our carbonyl, because we have this electrophile. We have the electrophile of the aldehyde ready to go. And the electrons will technically come up to the oxygen, but typically we see this as a concerted step. So instead, we're going to have it attack the phosphorus. And in doing so, the positively charged phosphorus there, and in doing so, we end up with this kind of square-shaped intermediate. We have our carbon here with its 2 methyl groups, and we have our original methyl group and our hydrogen from before. And then the arrows just move the same way again. So we're going to have the phosphorus-carbon bond break, forming a carbon-carbon double bond, and the carbon-oxygen bond breaks, forming a phosphorus-oxygen double bond. So the arrows happen again, which now will break our original carbon-oxygen bond. We'll end up with our oxygen now double bonded to the phosphorus, and we end up with our new carbon and whatever its substituents happened to be. So we end up now with these 2, and we have replaced that oxygen with the carbon-containing units. So with this reaction, it's quite simple. You'll take your aldehyde or ketone. Here's benzaldehyde. Why not? Let's treat it with. How about we have an isopropyl group? How about we have both of them as isopropyl groups? Because why not? If we do that, everything in the original molecule stays the same. So I can copy paste it. And we just erase the oxygen, and we put all the stuff that was on our phosphorus. So that now all goes right here. And I'm explicitly drawing in the carbon so we see that it is now a carbon there. And so, very synthetically useful, because forming carbon-carbon bonds is always tough, but we can do it now with predictable reactivity and, more importantly, as we'll see in the next video, stereochemistry.